When I first arrived in Madison for my interview in February 1994, John Kutzbach was instrumental in making me feel at ease with the magnitude of the opportunity with which I'd been presented. I recall fondly an evening tea at John's home during that visit and how comfortable he and Gisela made me feel. The hospitality and generosity of spirit that they both showed me was clearly derived of a desire to create within our department a family-type atmosphere. He'd recruited others in that crusade. David Houghton and John Young were near the top of that list, but were by no means the only other members. And as I look back on 27 years here and at the world that John Kutzbach has left for us, the surprising focus, the leading characteristic of my professional life here in Madison is that I view my colleagues as a family, with my eyes open wide enough to recognize that that's not something everyone on this campus could honestly say. And I believe it was the influence of John and Gisela that had a lot to do with establishing in my mind that one should feel entitled to such an expectation. One should operate with the sense that true scholarship cannot be undertaken in the absence of fellowship. In fact, all the laudable efforts surrounding diversity, inclusion, and equality that have taken on such high profile in our turbulent times are essentially rooted in this same expectation and cannot be achieved without the uncompromising respect for others that was modeled so persistently and vividly by John Kutzbach. So among his many contributions to our small community of scholars within this department, our broad discipline, and the world at large, I think the greatest legacy John has left us, and especially our young striving scholars, is the conviction that one should expect to work among colleagues who respect you and have your best interests at heart. This should not be an unusual circumstance, and the fact that it may still be unusual is a function of a deficit of commitment to each other, something that can always be remedied. John was a man of deep faith. To share dreams, triumphs, difficulties, and challenges with someone of his empathy, his wisdom, and his humanity has been a source of great strength for all of us who are lucky enough to find ourselves within his circle. And I'm comforted in knowing that John left us filled with a confidence that we would have many more conversations, explore many more mysteries, and continue to enjoy a friendship that we'd only scarcely begun to tap in our earthly lives together. Dan, you have some comments.
Thanks, John. As John mentioned, John was a remarkable person in our department and set a tone in our department. I think he was a mentor and role model for so many of us, and myself included. I will fondly remember walking down the hall and seeing his door open and that sense of excitement to know that I would be able to duck in and say hi and ask what he's up to. John was not only a mentor for me in my career, but in his role as a father to his family and as a husband to Gisela, he was a role model for me. At his service today, his children spoke of his empathy, his validation of others, his joyful approach to life, and his curiosity. I think all of us who knew him recognize and are inspired by those qualities in him. For those of us who knew John, I'd like us maybe later on this evening to take a moment and with our memories and remember and appreciate all he did for us. And for those of you who didn't have a chance to know him, I'd encourage you to think of others who play that same role in your lives, a role of inspiration, support, and a joyful approach to life. I had a chance to talk with John last Thursday, the day before he died. And he spoke in appreciation for his 83 years of health, his wonderful wife and his family, his faith, and a career that allowed him to pursue his curiosity. And one of the things that I think is really inspirational to me is that he spoke with excitement of the direction that AOS and CCR are going, especially with respect to new faculty. I expect he would be thrilled to see what will be presented in today's colloquium, with contributions from colleagues that have helped him build our department into what it is, and contributions from those who will take that and build into the future. Let's treat today's talks as a celebration of curiosity, a chance to support each other, an example the joy our scholarship brings to our lives. I'll miss you, John.
Thank you, Dan. So I think we'd like to move to our first speaker of today. And that will be who is in alphabetical order. Ángel, great. So Ángel, we're looking very much forward to your presentation, and you can start whenever you're ready.
Yeah. Hey, everybody. I'm here. Today's like one of those days that I'm like, I could have used some coffee. So hopefully, like, just as I talk to you, we all wake up together, right, and have an engaging discussion. So as the title suggests, I'm going to be talking about the Jigsaw Puzzle of the tropical atmosphere. And this title came after I saw this image that I found on Google, so it's like, as many of us discover things by Googling around, I found this Googling around. So maybe I'll get some kind of copyright thing at some point. But and I thought it was kind of cool because you got this tropical beach and the little puzzle pieces, and we all like puzzles. And I like to think about a lot of what's going on in tropical atmospheric dynamics research as kind of like trying to piece it together, a major puzzle that's been taking us decades to put together. So next slide. So cool. So if you've seen some of my previous talks, you'd be familiar with this animation. It shows different types of equatorial disturbances. And one of the things that is really kind of interesting about these animations, you see like the white stuff is clouds, like a cloud brightness, and then the contours are filtered for different types of equatorial waves or equatorial wave-like disturbances. And one of the things that you would see is that there's actually a lot going on in this region. You got different colors representing different things. For example, little red contours correspond to Kelvin waves, and then the blue light cyan contours the MJO, the big one, and you get Rossby waves, which are like in light blue. And you see that there's like a myriad of diversity. The Kelvin waves are pretty small. They kind of stipple on pretty quickly. And then the MJO is much bigger and kind of like crawls. It's a big mammoth, kind of crawls slowly. Actually, the Kelvin wave thing being small is actually relative. Kelvin waves, those red contours are about the size of California or even Texas. So they're actually quite big, and they're just small in comparison to the MJO, which is like the size of Russia. So, but they're important. They have different scales and they modulate weather in different ways. Next slide. Oh, so okay. So one of the things that gets us all riled up and confuses us is that there's a lot we don't understand about the tropics, and a lot of the things that are going on that cause confusion have to do with clouds, and particularly convective clouds. So this is a diagram that never got published. This is like version 28 of a schematic that ended up being 70 versions, and this schematic shows kind of what you kind of see in like these convectively coupled disturbances. You got a big large scale circulation like on the bottom and the top, and you got the clouds that are kind of like interacting with the circulation, and you have all these things happening at about the same time, and they're very complicated. And then you add on that the ocean, which is important too, especially positive to the MJO for like El Nino and all that, and they're all interacting all the time in very complicated ways. So this is the stuff that kind of like really is the reason why progress has been very complicated and slow to happen. Next slide. But there are some theoretical considerations that are coming together that are indicating that there are some building blocks that are actually suggesting that things are coming together, and that there are some large, big, broad ideas that are kind of like helping us understand things in a more broad context and how these things are interacting. And this is a pyramid from a paper that's in review. I just got the reviews today again, but still in review, in revision now. And it shows that different types of waves exist, and they're actually interacting with one another based on some simple parameters. The well-known Rossby number that you all see in GFD and dynamics classes is on the right, and that kind of like separates the gravity waves from like the Rossby waves and everything in between. And then specifically in the tropics, you get waves that are driven by variations in water vapor. And when the atmosphere is saturated, which is like this gross moist stability stuff, you get what they call moisture modes. And then everything in between also exists. So next slide. And hopefully, once we get all these ideas together into something neat and pretty, we can use these things to describe, do some better forecasting, and understand how the tropical atmosphere interacts with the mid-latitudes and how all these things are going to respond to increasing CO2. All right, done.
Wow. That was right on. That was 30 seconds early. Questions for Ángel?
Excellent.
This is Tracey. I have a question. Hi, Ángel. Nice to see you.
Nice to see
and
you
I was
too.
wondering, in terms of sort of where you see the big questions in this area, is it, what do you see as sort of like the big mission that your goal is to, these are to pull all these big ideas together?
So I guess one of the big questions is like, is there a way that you can like distill the properties and the interactions between clouds and the large scale circulations in a way that you can like simplify it and like in some kind of statistical way? This is a much bigger task that what what it sounds like from me just saying the sentence, because you got really important interactions that are coming around and are being important. For example, radiation in clouds are interacting really important ways in the tropics. There's also like development, the clouds can humidify the atmosphere, and then that kind of like leads to more clouds, etc. But like I would say that that's probably like the big question as to like, is there some statistical behavior that is common to like all sorts of organized systems that we can put together in a meaningful way, in a simple, meaningful way?
That's exciting. Thanks.
As a question from Dan, you mentioned the intersection between mid-latitude and tropics. How do you envision your framework can characterize the interactions between the two?
I don't know. Maybe that's a conversation for like people like John and myself and other tropical people, mid-latitude people, who sit down and figure out.
Yeah, that sounds really fun. In fact, I had a question I think has some relation to that, Ángel. When you were showing all of the puzzle pieces on your first slide, the Rossby waves, the MJO, and the Kelvin waves, is there a way to assume, or is there any benefit to assuming that they do not interact with each other versus diving into the complication of the presumed reality that they actually do?
So I guess like if you want to like get the broad idea of where are like, for example, like let's assume that like the triangle, right? So you assume that the edges, the vertices of the triangle exist first, and then you kind of want to like figure out what's in the middle. Like the edges are actually way easier to figure out than what's in the middle, because they kind of like represent like extremes.
Yeah. Okay.
And then the middle is kind of like all the complicated stuff. So if we want to understand the middle, we kind of want to understand the edges first. I don't know if that makes sense.
I think I have the idea. So yeah, getting a sense of the extremes can lead you to something about interactions if you start to study how they go into working together. That's very interesting.
That's right.
I know. I have a quick question. It's
Yeah.
kind of related to the one that you just mentioned. So when you looked at that triangle diagram with the Rossby number, the gross moist stability, and I can't recall what the other axis was, or perhaps it wasn't another axis, is there sort of a rigorous scaling that allows you to identify each of those blocks uniquely, or is there a lot of overlap on them?
Yes, I actually have like a lot of that like written down, and like this is part of a paper that's in review, and we discussed the scaling. I also have a 2019 paper that discusses the scaling. I don't have a paper that should come in the future that kind of like does the scaling for the whole triangle together. That's kind of like the goal eventually, to like have something that has the whole triangle. Like we've like colleagues and myself have been like kind of like doing the scaling for the different sides of the triangle. But like to do the whole thing, you need like full all of the equations. You can't like simplify. For example, like the lower side is like the more balanced, which you can assume some kind of quasi geostrophy or some kind of balance dynamics, but you can't assume it for like the top part. So you need to like assume not assume anything for the whole thing.
Okay, very exciting. Thank you.
Yeah. Thank you, Ángel. Okay, we'll have to move on to our next speaker. And that's Professor Matt Hitchman, who's going to talk to us about some of his current thinking about the stratospheric QBO and the tropical and subtropical upper troposphere and lower stratosphere. So take it away, Matt. Matt, you might be muted.
Am I still muted?
No,
You're good
not
now.
now.
You're good now.
Thank you for this opportunity to give a brief description of this. This is a culmination of about 22 years of effort, actually. 22 years I started on this project. And also, I'm hoping that next fall I can give a colloquium on this and give a much more complete explanation. So you can see I put in a couple of acronyms in the title. So now we know the QBO is the stratospheric quasi-biennial oscillation, and UTLS is the upper troposphere and lower stratosphere. And the basic idea is that the QBO is an entity that spans a great range in height and latitude and is a simultaneous occurrence in all these locations. So that's sort of the integrative concept here. I really should have emphasized my co-authors in black here. They're Shigeo Yoden, Peter Haynes, Vina Kumar, and Suzanne Tegmeyer. She just moved from Europe to Saskatchewan, and she'd be a really good person to invite for a colloquium, I think, next fall. And here's the little logo that we designed for this project, SATIO TCS, and it illustrates it's during a phase of QBO easterly where there's antiphased manipulation of the tropopause and possible influence on tropical and subtropical jets and cloud systems. So that's the basic approach here. Next slide, please. So you know about this. This is Reed et al. And also Verrier and Ebden in 1961 discovered the QBO, where we have alternating layers of descending westerlies and easterlies that go on forever and ever, world without end, except 2015, where the westerly descent was interrupted briefly. The range here is some 35 meters per second. And one thing I want to point out is the tropical tropopause is nominally 17 or 18 kilometers, right? 80 hectopascals perhaps. So you can see that the QBO definitely penetrates the upper troposphere. And this has been the nub of the debate for the last 20 years, where Amihan Huseman and I said, well, we think there's some influence into the upper troposphere and into the subtropics. And we published some of it, but now the rest of it is being published, and I'm very glad. So next slide, please. And we discovered a lot more new things, and it was really great to work with other people. So here's the basic idea. I first thought about it when working with Chip Trepty, who got his PhD in this department, studying stratospheric aerosol, where we could look at the QBO. And the idea is that if you have a descending westerly where waves are being absorbed and spinning up the flow, that'll actually cause Coriolis torques, which are convergent, and a mass circulation like this. So you expect, from theory, a meridional circulation that could warp the tropopause in this fashion, downward in the tropics during QBO westerly, upward in the subtropics during QBO westerly, and then the opposite phase during QBO easterly. But this is just a surmise from theory. This is just from theory. So up until this paper, there has never been a quantified depiction of this circulation. So that'll be the last slide that I'll show. You notice figures 1 through 9, there's a bunch in between. So we go through the stages of evolution of understanding of this problem, but we'll have to wait till the fall to hear about that. Next slide, I'd just like to show 3 results. And the approach here is to just bin QBO westerly and then periods of QBO easterly and form the difference for various UTLS quantities such as temperature, pressure, and zonal wind. And the first thing that we did was we used NCEP data for these 2 time periods, 58 through 78 and 78 through 2000. And well, I'll tell you the story of the publication trials and tribulations some other time, but I'm glad it finally worked out. And the whole key was to work with these other co-authors, and they had access to these data sets. Okay, thank you, John. We looked at MERO data and also ERA interim data. So next slide. This is our original result, and this is just for December, January, February. For tropopause temperature at NCEP, we found 1 to 1.5, maybe 1.8 degree Kelvin range in temperature of the tropopause. And this was validated in ERA interim data for 100 hectopascal temperature. And in this technique, we used empirical orthogonal functions 1 and 2 for the vertical distribution of winds. This is a technique pioneered by John Kutzbach in 1967. He put use of EOF on the map for everybody in meteorology. And then this pattern was also verified by MERA-2 data using cold point tropopause data. So these 3 different data sets, 3 different techniques show interesting geographical and seasonal variations. Next slide. Just a couple of other examples. We also found in the year 2000 that the tropopause pressure on the winter subtropics and also the subtropical westerly jets are modulated by the QBO. This is southern winter. The tropopause is some 500 meters lower. Tropopause pressure, 500 meters higher, 6 hectopascals lower pressure. That's interesting. And then this last example is, I'm astonished. Okay, so March, April, May, you can see the antiphase temperature structure in ERA interim at the tropopause. That's understood, plus a geographical dependence. But for the zonal wind, look at the 5 meter per second enhancements of the northern and southern subtropical westerly jets. This is the first time this has ever been shown by season and geography. And then a diminution of the Walker circulation. This is at 150 hectopascals during QBO westerly. Next slide. And so this is the last result slide, figure 21. And on the right is QBO temperature. This is drawn for QBO westerly minus easterly, so there's a warm anomaly. Here's the cold anomaly that shows this structure. And I don't know if you'd call this a tic-tac-toe pattern, but we also have the meridional and vertical motions in this. And on the left is the zonal wind distribution. And there's a statistically significant zonal wind QBO in the deep tropics throughout the troposphere. Okay, all right, last slide, please. Some conclusions. QBO westerlies favor a warmer subtropical UTLS and at the same time a colder subtropical UTLS. There is a larger temperature signal near seasonal convective centers, which is interesting, and it's consistent with both the temperature and wind shear hypotheses for how this interaction could occur. The subtropical signal is enhanced during March, April, May in both hemispheres and in the winter side, June, July, August, and southern, and December, January, February in the northern hemisphere. And then to fix ideas for QBO westerly, we have enhanced subtropical westerly jets, and the Walker circulation is reduced. And this effect is strongest during March, April, May. And lastly, this is the first quantitative depiction of QBO structure and temperature, zonal wind, and mean meridional circulation, thanks to my co-authors. Data processing.
Thanks, Matt. We've got maybe time for one quick question.
Hi, Matt. What is the temperature convection hypothesis that you mentioned? Can you mention a little bit more about that?
So to the extent that we can think of a thunderstorm or a tropical cyclone or a convective cluster as an engine having a certain efficiency, there are various papers, perhaps dating back to Kerry Emanuel's idea of thermodynamic efficiency. If you have a colder, higher tropopause, it's speculated theoretically that there's a greater efficiency for cloud clusters to grow.
Okay.
And that happens during QBO easterly, and particularly over Indonesia. And it's consistent with effects on the MJO during that period of time as well. You know, QBO easterly facilitates a stronger, slower MJO. Probably interacting through the maritime continent convection itself.
Yeah, that's what I'm wondering. Yeah, cool.
Okay, we'll have to move on. We're looking forward to the longer version, Matt, in the fall. Thanks. That's really interesting. So we'll move on now to Tracey, who's going to tell us what she's thinking about air quality and energy and public health. So Tracey, take it away.
Thank you, John, and thanks everyone for coming. It's really a pleasure to be here and giving you this kind of 30,000-foot perspective on some of the work that I'm working on now. Next slide, please. So I wanted to just start out with a shout out to my research group, in part because I think it tells a lot about the kind of work that we're doing. I work with quite a few AOS graduate students and undergraduates, along with AOS alum Monica Harkey, who's been a researcher in my group for about 10 years. But I also work with students from lots of other departments. One time I counted it up, and I think 15 different majors of undergrads had done work with my group. And we also have a lot of expertise in communications and topics that are sort of one step away from my background in AOS, like energy modeling and public health. So it's been, I think one of the best parts about science is getting to work with such an exciting group of students and colleagues, including everyone here in the department. So I just wanted to start out by kind of an introduction to the people behind the work that's going on. Next slide, please. The big picture work of my group uses satellite data and air quality modeling to connect air quality, energy, and health. And we have a number of different projects going on. And I'll just kind of give you a high-level summary of a couple of those here, drawing from information on my group website. Of the projects that we have going on right now, one is we're working with Madison Gas and Electric to analyze model data in a way that's useful for their corporate decision-making. We also are working with states across the Midwest to calculate what the air quality and health impacts would be of climate and energy policies under consideration. Because anytime you move away from fossil fuels, not only do you reduce carbon, but you reduce ozone, particulate matter, and have a lot of valuable health benefits. But these benefits are not typically included in climate policy making. So we're doing modeling to support states across the upper Midwest. But one of the biggest projects I work on is leading the NASA team to make satellite and other science and tools available for air quality and public health. Next slide, please. This is the NASA Health and Air Quality Applied Sciences team. And I led this team in its first manifestation from 2016 to 2020. I was really excited just a few weeks ago to find out that I'd been selected to be the leader of the team starting this year and going through 2025. And our goal is to answer research questions that make science from NASA and satellite data especially more usable by organizations on the ground. And one thing I found exciting is that actually there's a lot of valuable research questions that come out of these applications, because often organizations want to use data and methods in new ways. And then there's a research question: can it be used in that way, or how good is it for that new question? Next slide, please. So just to skip over a couple other projects that we're working on, I'm collaborating with Tim Bertram in the chemistry department to take some of the chemical mechanisms that his group has proposed and integrating them into the EPA state-of-the-art model for air quality. We have a grant from EPA that just started doing that. I'm working with the state of Texas to evaluate whether satellite data can be useful for their air quality planning. In particular, thank you, John, evaluating their emission inventories. They have estimates of chemicals coming out of cars and trucks and power plants, but we don't know if those are the right estimates. And they want to know if satellite data can help constrain that question. And finally, I have a project in collaboration with Dan Weinmont and working with recent AOS master's student Gesayanji to use climate model data and apply that to building codes and specifications with the support of the UW-Madison Office of Sustainability. Next slide, please. Beyond that, I do a lot of work with the Energy Analysis and Policy Program, which is a graduate program that's open to almost any graduate student. So if you're interested in energy or policy or both, check out eap.wisc.edu. Next slide, please. And I also do a lot of science outreach. I run a program called Science-a-thon, which has scientists share their day of science on social media. And recently I've gotten involved as one of 6 science moms, trying to be kind of like the weather guys are for weather and guys. The science moms are trying to be for climate science and being an accessible point of entry for anybody in the public, but especially moms who wants to learn more about climate science. And in fact, I was on the Weather Channel on Saturday morning at 6:40 talking about the Science Moms effort. Next slide. And I'm done.
Okay, thank you, Tracey. We've got about 2 minutes for questions, so let's fire away, audience. Okay, I'll prime the pump, Tracey. I'm always interested in outreach issues. How do you start them? Where's the first step that you went to start thinking about the Science Moms idea? Who'd you talk to first? How did you get it moving?
Yeah, so it's a great question. And I'll say that actually Science Moms was launched by a group led out of Harvard, and Catherine Hayhoe at Texas Tech was kind of the first science mom, and she pulled me in. So I think the real answer to that question, John, is kind of that I've been doing science outreach for a long time. So when an opportunity like this came along, I think Catherine knew that I'd be interested and excited to participate. And for me, it's been something, you know, saying yes to speaking to the Girl Scouts and local schools, getting involved in social media, taking training opportunities when they came along, and kind of just slowly trying to build my skills and my comfort with outreach so that I got on the radar of other organizations doing outreach. But also then, you know, when I show up on the Weather Channel, that I don't totally feel like I'm a fish out of water, that I've done things kind of like that before, although that was pretty exciting.
Yeah, yeah. Any other one last quick question for Tracey?
This is Brad. Tracey, I know you founded the Earth Science Women's Network. Could you talk a little bit about how, what's the intent there? Is that something that students can join?
Yes, absolutely. In fact, anyone can join the Earth Science Women's Network, men or women, any gender, any level. The website is eswnonline.org. And I founded that when I was a postdoc working with some colleagues, and we realized that there were a lot of mentoring needs that we had that weren't totally being met by the current structure. So really ESWN started as a peer mentoring program. And since then, it's gotten involved in a lot of different training, outreach, engagement with the scientific community. I'm no longer on the board, but the outreach program I run, Science-a-thon, is part of ESWN, and 10% of our revenue goes to support their activities. And I'll just say, last time we checked, of all the different fields of science in ESWN, atmospheric science was the biggest component because we were all atmospheric scientists who founded it. So I'd really encourage anyone in the department to join, and I appreciate the question, Brad.
All right. Thank you, Tracey, for a lot of interesting information. And it's nice to know what your program's doing because it's so big. We have to move on given the constraints of the program. Thank you. And next, we're going to hear from Tristan, who's going to tell us about Pre-Fire, which is, I think, a relatively new program that's about to really fire up. But Tristan, I'll let you tell us. Go right ahead.
Yeah, sure. Thank you. It's great to see such a wide diversity of great science going on in the department. So yeah, I'm going to focus on talking about this relatively new project, or I guess we're about a couple of years in now to the development of the polar radiant energy in the far infrared experiment, it's called. This is a NASA satellite mission that's I'm referring to as a new frontier in Earth observation, hopefully for reasons you'll see here in just a moment. Next slide, Zoe. Thank you. So the story begins kind of here. This actually shows probably about 50% or so of the research in my research group, which is focused on understanding polar energy balance. So this is a result that's in a paper that's in preparation by Marianne Maitling and myself. And I don't want to spend a lot of time talking about the specific numbers on the diagram, but I just want to remind everybody that the poles play a really important role in the Earth's climate because the poles radiate heat to space more than they take in from the sun. And so that drives transport of energy from the lower latitudes into the polar regions and is really responsible for a lot of the circulations we see on the planet. And Zoe, if you click twice more. Yeah, so the one thing I want to focus on is these red bars, which represent the thermal exchanges of energy between the surface and the atmosphere and space. And you don't have to look at those numbers, but the main thing is if you look at our best estimates today of the thermal heat exchange between the surface and the atmosphere and the surface, you find that there's a wide range of estimates. There's a lot of uncertainty, whether you look at weather models, climate models, or even observations. So one more time, Zoe. So pre-fire, the goal of the mission is to reduce the uncertainty in these thermal fluxes in the poles, and hopefully in doing that, improve our ability to predict polar climate and also global climate. Next slide, please. And just as a sort of a primer for what pre-fire will do, here's why I think there's so much uncertainty in these thermal fluxes. So this is just a sample Greenland emission spectrum from the center of the Greenland ice sheet. And if you click one more time, Zoe, this is the fraction of that spectrum that's actually observed with current satellite systems. all wavelengths longer than 15 microns, which is what we call the far infrared, are not observed with today's platforms. And so we were really lacking about 50% of the information regarding the emission spectrum from most of the polar regions. And that energy carries the fingerprints of things like surface properties, water vapor, and cloud properties. If you click one more time, the map at the bottom there, without going into a lot of detail, just shows the fraction of the global emission that comes from wavelengths longer than 15 microns that we don't observe systematically with current satellites. And so you can see almost everywhere on the globe, it's more than about 50%, with the exception of maybe the deep tropics where it's still 45%. So we're missing a lot of information about the emission spectrum of Earth, and we're missing a lot of information about key processes in the climate system as a result. Next slide. So the goal of PREFIRE is to fill this gap. And what we're going to do is measure spectrally resolved fluxes at relatively coarse resolution, about 1 micron resolution, but from 5 to 54 microns instead of stopping at 15 microns. And the exciting thing about the mission is we're going to do this using a miniaturized infrared spectrometer on 2 CubeSats. These are satellites about the size of a cereal box. And so the fact that we're able to use such a small platform to make such a critical measurement is really exciting. It's kind of a new frontier, as I call it, in observing the Earth. If you go on to the next slide. And this is the concept. We're basically going to fly 2 of these cereal boxes around the Earth in polar orbits, distinct polar orbits. We're going to map the far infrared spectra of the whole globe, but especially the polar regions. And then by having 2 CubeSats, if you look at the lower right-hand corner of the slide, we're going to use intersections of the 2 satellites at time intervals between 0 and 12 hours to actually understand the processes that shape the emission spectrum of the Earth. So things like melting of the ice sheet or things like cloud formation, we'll be able to understand how that affects the spectra and how that affects the Earth's climate. Go on to the next slide, please. I'm not going to go into a lot of details about the hardware. We're in the process of building this now to the extent that COVID will allow it. I did just want to point out the dimensions of our instrument, though. So if you look at the panel C there on the lower right, you see that our instrument is about 13 centimeters long, 9 centimeters wide, and 12 centimeters tall. So it's a small instrument. It weighs 3 kilograms and uses about 4.5 watts of power. So we're able to make these important measurements using, again, these small CubeSat satellites. And then the last slide. The other thing that I find really exciting about the mission, and it really gets me energized, is that we have a series of both process modelers and climate modelers on the team. And so we have a plan to directly incorporate our observations into process models like ice sheet melt models and global climate models. And so hopefully, shortly after we launch and we make our first measurements, we ought to see a direct impact on our ability to predict the evolution of the Arctic and polar climate. So that's all I have. Thanks.
Thank you, Tristan. Any questions for Tristan? We have about 2 minutes for questions. Well, I'll start them again, Tristan, if you don't mind. I'm interested to know if these little cereal boxes are doing both remote sensing of radiation from the ground, the atmosphere, and clouds, or some subset of that triad.
Yeah, so it's going to be all, we're basically going to make continuous measurements as we orbit the Earth. So we're going to measure all conditions. Under clear sky conditions, we will get direct measurements of what is coming off the ground. Under cloudy conditions, we'll get measurements in cloudy conditions and measurements that will be conducive to retrieving the properties of thin ice clouds. And in clear skies, we'll also be able to retrieve water vapor concentration, so some aspect of the atmosphere besides clouds as well. So we ought to be able to characterize both the surface emission and the processes in the atmosphere that influence that emission.
Okay, I've got one from Grant. I'll read it. What do we currently think we know about the variability of the emissivity of snow and ice in that spectral range that's kind of clouded?
Yeah, that's a really good question. So what we think we know, and that's based on mostly theoretical calculations and some laboratory experiments, is that the emissivity might vary by as much as 20% between fresh snow and open water and also bare ground. And so the emissivity may drop to as low as about 80% at certain wavelengths in the far infrared. But again, that's all based on theoretical calculations, and we don't know, first of all, the frequency with which those low emissivity values occur, or how they really map out spatially in the polar region. So pre-fire ought to do that.
Okay, thanks. And Dan's got his hand up. Dan, quick question.
Yeah, I was shocked to see the 45% in the tropics as well. What is that? Those numbers, 45% versus 65%. What does that translate to in terms of uncertainty in, say, watts per meter squared, and how much do you think will be of that uncertainty will be addressed with pre-fire?
Yeah, well, to piggyback on Grant's question, we've done some simulations of what happens when you assume a constant emissivity from the mid-infrared and just extrapolate to the far infrared. And we think those uncertainties could be at least on the order of 10 to 12 watts per square meter on a global average. Now, of course, locally and under short time scales, it will be a lot larger than that. And also the fact that you mentioned the tropics, I'll add that the pre-fire measurements ought to have information about lower stratospheric water vapor and upper tropospheric water vapor, which is another large uncertainty in climate, not necessarily for radiative reasons, but also more for, kind of weather and water cycle reasons. So we ought to hopefully be able to constrain some of that as well.
That's amazing. Thanks.
All right, thanks very much, Tristan, and for the questioners too. And we'll move on now to our next speaker, please. And that is Michael's going to talk about seeding, and he's going right to the background. Seeding an initial condition-based ensemble, how to make useful ensemble prediction system. Michael, take it away.
Thank you, John, and thanks for the opportunity. My apologies for having to have this talk from last week moved to today. So my talk today is on making a useful ensemble prediction system. I'll be describing some issues related to predictability and some initial progress we've made. This is work that I've done with my graduate student, Carrie Marr at Ledesma Maldonado, as well as Brett Hoover, a scientist in SSCC SIMS. Next slide, please. So when we talk about the issue of predictability, one of the key things to recognize is that predictability is flow dependent. So that means a 3-day forecast from today may or may not be as accurate as a 3-day forecast made 2 days from now. And so the flow predictability is something that you want to be able to predict. How predictable is the forecast? So for most forecasts, knowledge of these forecast uncertainties adds value to the forecast consumer. Single deterministic NWP model forecasts don't provide that information, particularly the associated uncertainties with the forecast. However, collections of deterministic models of forecast can provide that information. And there are a number of ways that you can use to create these so-called ensembles or collections of forecast. Some may be created from varying the initial conditions or the boundary conditions, the model physics, or in fact, combinations of all of these differences. My talk today focuses on initial condition-based ensembles. Next slide, please. So the motivation for this is that small changes in model initial conditions can change a forecast. That's kind of pretty well known. Some of these changes will grow over time, but most others will decay. So if you want to seed a forecast to create ensemble prediction, just putting random perturbations in the model will perhaps not give you the variability in the forecast that you seek. The seek to seeding an ensemble with initial conditions is to identify those perturbations at the initial time that will grow. And in fact, if you can identify those that grow most rapidly, that will allow you to get a broad spread in the forecast from which you can hopefully assess elements of the predictability of the flow, creating a probability of predictability exceedance, or perhaps coming up with forecast scenarios. On the slide that's shown right now is the Lorentz system. It's a series of 3 differential equations, ordinary differential equations, nonlinear. And on the right, you can see a sample solution from this when you choose a certain set of parameters for rho, sigma, and beta. And you see that the solutions lie on a particular phase plane where the solution is tied. So for the so-called Lorentz ensemble, imagine taking an initial ball of forecast or initial condition uncertainty, that's the red circle, and along the radius of that red circle, it's supposed to be a circle, we're basically making perturbations of equal magnitude in the 3 variables in the forecast. As you project that forecast forward in time, projecting each of those points, you can see that initial circle begins to deform into an ellipse. And the fact that it deforms into an ellipse indicates that there are certain directions in the phase space of the model in which errors grow or uncertainty grows, and there's certain directions in phase space in which they decay. In this 3-dimensional example, which is perhaps the best I can do for you, the circle deforms into an ellipse. If you look at this in n dimensions, it will be a hypersphere deforming into a hyperellipse. The major axis of the ellipse indicates where there's a growth in forecast uncertainty. The minor axis is where things have compressed. And so one of the big issues is, can you identify, if you know what the final time structure is of the evolved uncertainty, if you know the major and minor axes at the final time, how do they relate to initial condition perturbations that you could put into the model, which I call V1 and V2 on the left side of that. So V1 evolves into U1, V2 evolves into U2, and how do you actually calculate those? The perturbation V1 in this two-dimensional plot is that perturbation that evolves most rapidly to become U1, a rapidly initial growing perturbation. Next slide, please. So the way we calculate these are singular vectors. The initial vectors, which I've called V, are those that are so-called the right singular vectors of the tangent linear model L. And you can calculate them by solving an eigenvalue problem for the matrix L transpose L, where L transpose represents the adjoint of your forecast model, and L is the tangent linear model. Now, for very simple low-dimensional systems like the Lorentz system where n is equal to 3, that's fairly easy to do. But the challenge is trying to do this for a system like the Whorf model, where you have 10 to the 6th or 10 to the 7th points in your state vector, and how to create that. So the next slide, please, thank you, shows an example of such a calculation. It's rather crude initially, but the sigmas that are shown there are the growth rates of the perturbations. And we've done this with the Whorf model with about 40 iterations back and forth with the solver that we're using, which is so-called Lanczos algorithm. And we're looking at a case from an East Coast storm from last December. The pink isobars are from the control forecast, the green are the perturbed, and then I have colored sea level pressure differences in the fill pattern. And you can see this gives, for the first and second singular vectors, gives you some patterns, some scenarios for the flow. One would be a much stronger storm parked over eastern North Carolina and Virginia, or it could be a much more rapidly departing storm or weaker storm over the just south of New England on the second singular vector. By doing this calculation and calculating all, or not all, but many of the first sets of singular vectors would allow you to take your initial conditions, project them forward in time with a nonlinear forecast, and then come up with ways of assessing, again, probabilities of exceedance of precipitation, or developing forecast scenarios of a storm going out to sea, or the likelihood of it remaining close to the coast and what those impacts are. So this is more looking at forecast for forecast consumers. The dynamics of these singular vectors were described back in my colloquium talk on September 10th of 2001 on embracing uncertainty and understanding the dynamics of those. Now we're trying to explore how these actually can be, we can exploit these singular vectors. Thank you for your attention.
Thank you, Michael. We've got time for maybe one long question and one short one.
I have a short question. This is Brad.
Yeah, sure, Brad.
So you seed to get the fastest growing perturbations. It seems like that might overestimate the uncertainty. Is that related to the model overall underestimating uncertainty, or why do you want to find the fastest growing?
Well, the idea is if you put random perturbations in, most of them are probably going to decay. And so you want to find ones that will at least give you some spread, because typically models, ensembles, whether you use initial conditions or you use model physics to perturb them, they're under-dispersive. So you want to try to increase the dispersion to get the outlying types of events. And you don't just get the first couple, you can get the first 50 like ECWF does. And so we've done this with the Whorf model, or beginning to do this with the Whorf model. You'd like to get some spread in the forecast to assess the predictability of the flow.
Thanks.
Angela, you had your hand up.
It's a bit of a longer question, so I may actually just follow up with Michael afterwards.
Oh, okay. Okay.
Yeah.
Then I think we're at the end of the 7.5 minutes, so I think we
Okay.
should move on.
Thank
You, Michael. And now we go to Angela's presentation, Improving Understanding of Global High Impact Weather. So Angela, it's your floor.
Okay, thanks. Yeah, this is kind of a broad level presentation as well, just to give a sense of some of the projects I'm working on and that are upcoming that approach this very broad topic, but from the specific way of using field observations with a combination of models, in particular focusing on convection across many areas of the world. Next slide. So when I first got here last year, before things shut down, I gave a seminar on Relámpago. And just to remind everybody, this was a field campaign in 2018 and 19 in central Argentina, with a purpose to observe what we think are some of the most intense storms in the world. And that's in terms of the depth of the storms, the frequency of lightning, and the hail, as you can see from this picture of some of the hail that falls in this region. And our group's goal in particular is, we wanted to observe and understand the complex interactions in this area between the terrain. The mountain range in our area is a small mountain range, the Sierras de Cordoba, just east of the Andes. And it's a global hotspot for convection. And we wanted to understand the interaction between the terrain, the environmental conditions of this area, and particularly how it relates to rapid upscale growth of convection. Because compared to the US, where you could have a very long area and long period of time where convection grows, say a mesoscale convective system, in this region, it tends to happen faster, almost as 3 times as quickly, and remains tied to the terrain in some instances, including backbuilding. So this is a prime spot to look at convective processes in general, and a great area to bring in a bunch of assets to observe them. So this just shows an example. The plot on the left is a vertical cross section from some of the radar data that we brought into the field that shows the depth and intensity of an example of one of these hail producing storms of the mountains. And since my last presentation, one of the things that I've done is use that radar data to do something as simple as look at the evolution of the storms, because before this, most of our data was from snapshots of, say, trim that gave us a general idea statistically how these storms may present themselves in depth and in time. But this allows us to actually do continuous evolution of these convective systems. Next slide. So just very broadly, just some simple questions to start is when and where do intense convective cells occur relative to the SDCs? And can we fill in some of that temporal gap that we had from satellite data? So one of the things we do, we can just use the continuous radar data over the course of 6+ weeks to look at individual cells when they initiate, how they evolve, track them in time. Sometimes they form just over the mountains, intense convection in the afternoon that decays. Sometimes they propagate off the mountains, but stay near the mountains enough that we can capture their full life cycle as they grow into large mesoscale convective systems. And this initial analysis using the radar data corroborates much of the satellite information in the sense that there's a diurnal cycle where the large MCSs tend to occur on the adjacent plains just near the terrain overnight and into the morning. But one of the things that this data set revealed within this time evolution is in the intensity of these cells that you can get just as equally intense convection over the terrain that initiates over the afternoon as you can get in some of these nocturnal MCSs. And when you get the most intense convection over the plains, this tended to occur during these multi-day episodes of convective activity. So we would get days upon days of convective activity, including some serial upstream propagating events that could last for over 12 hours. So this work largely is being done by a graduate student that I'm still working with at University of Washington, Clayton, who's writing up his analysis on the role that the South American low-level jet plays. This project also allowed us to have for kind of first of its kind observations of the jet in this region, and we'll be looking into how this influenced convective growth. And then Anthony Crespo here at UW-Madison is looking at a hail analysis of some of these upscale growth events and supercellular events. Okay, next slide. So that's been a lot of my current research and really diving deep into data, but I just briefly want to mention some other projects that are coming up. We're moving to Taiwan to look at heavy precipitation in this region. This project was supposed to happen last year, then this year, and now it looks like it's going to be delayed again until next year. But again, we'll be deploying radars to look at the role of topography in these very heavy rainfall events. And Ian Corneo here and the department is in the meantime using operational radar data from Taiwan to look at an event that occurred in 2017 where over 600 millimeters of rain fell in under 12 hours over Taipei Basin. So this project looks at this ingredients-based approach to heavy rainfall in an area that receives heavy rainfall, extreme heavy rainfall, from everything from afternoon thunderstorms to frontal systems, mesoscale convective systems, and typhoons. Next slide. And we also have another project where we're looking at tropical convection off the west coast of Africa. Again, this was a project that was supposed to happen last year. Hopefully, maybe later this year, we'll see what happens. But this is an airborne project, which has a unique combination of radar and a Doppler wind LiDAR. So it gives us a unique opportunity over the tropical oceans to look at the wind flow patterns in the vicinity of convection and start to look at some of those relationships between outflow and inflow, environmental characteristics along with the convection. And Ben here in the department is working on that project, looking at some data that was collected over the Eastern Caribbean with similar data sets as we prepare to look forward to hopefully a successful project later this year. So I'll stop there. Thanks.
Okay, thanks, Angela. We have time for a couple of questions for Angela.
I have a quick question. So Angela, why do you think the diurnal cycle looks the way it does in the Relampago observations?
Yeah, so one of the things that we notice is, you kind of have the diurnal heating cycle where you get the deep convective initiation over the terrain. And then with time, we see the MCS is often occurring with this nocturnal low-level jet, kind of similar in a way to the US and a similar diurnal cycle. But the distinction here, and I think what a unique attribute is the relationship between the jet, the convective generated cold pools, and the actual SDCs themselves, and how that really creates this unique longevity and backbuilding that occurs well into the day. So there are some commonalities in the diurnal cycle relative to the US, but I think the more intricate details are related to the unique topography. Does that address your question?
Yeah, I was just wondering why, I mean, you can answer for the US too, why the diurnal cycle looks the way it does.
Yeah.
I was just wondering.
Yep.
Juliet, a quick question.
Yes, hi. I was curious. Oh, sorry, I don't think you can see my video. Oh, I was curious if you have related at all the intensity of the convection that you're seeing to any other characteristics of the storm, such as rainfall amount or perhaps like even size or core features.
Yeah, that's a great question, Juliet. So one of the things with our radar analysis, we're looking at intensity in terms of different metrics, in terms of hydrometeor characterization and the height of which, say, grapple is observed. We're looking at the area of the system as a whole. So are these convective cells embedded within larger mesoscale systems? We haven't incorporated rain rate yet, just because we're still working on getting a reliable rainfall data set by combining all the different radars in the region. But that's something we can connect to it in terms of rate and total amount. And then we are also bringing in some lightning information as a metric. We had a lightning networks that was observed, as well as multi-Doppler synthesis to look at some characteristics of the updraft. So there's kind of a lot of pieces that are integrated within that, moving beyond things like reflectivity, height, and area, but adding other data sets to characterize the intensity.
Great, thank you.
Yep.
Thank you, Angela. And we'll move on to our next speaker. And that will be Till Wagner, talking about icebergs from North America to Morocco during the last glacial period. Very interesting. Till, take it away. You may be muted, Till. I don't know.
Hi.
There you are.
Can you hear me now? Sorry.
Yeah, you're in. Great. Okay. Thank you.
So I picked this little story because I thought it would be a nice thing to tell in 5 minutes. And just as a disclaimer, this is a photoshopped picture. It's not actually an iceberg in front of Morocco. So if you show me the next slide, please. So, the colors have changed. This used to be red dots. So in the last glacial period, there was a giant ice sheet, the Laurentide ice sheet, over most of North America. And at certain intervals during this past glacial period, there were events where the ice sheet shed a ton of icebergs suddenly over the course of like a couple of 100 years. And that's sort of indicated by these arrows. And the events were called Heinrich events. And we know this because we find sediment from the Hudson Bay area all over the North Atlantic. And so the sediment the sediment is contained in the icebergs. And there's a little picture of what that looks like on the bottom right here. And so as the icebergs melt, they leave that sediment. And we know that those sediments have to come from the icebergs. So that's called an ice rafted debris. Next slide, please. And so what we try to do is reconstruct that using models, this dispersion of the ice raft debris. So at the top here, you see trajectories. I previously developed an iceberg drift and decay model, and here I'm using CCSM4 GCM conditions to force my model. And on the left, we have trajectories with forcing from the 20th century runs. And you can see that the icebergs sort of make it halfway across the Atlantic. And then on the right, you see the same model, but now forced with LGM conditions. And interestingly enough, the icebergs didn't actually travel in my model much further than they did in the 20th century. In the bottom two panels, you see the freshwater distribution from these simulations, and you can actually see that they are pretty similar between the 20th century and the LGM. Next slide. So to highlight this point, I've taken the meridional averages and plotted sediment depth versus longitude here. So the ice rafted debris proxies from the sediments you can see on the top, those circles. And you see that they, as you go from west to east, they drop down very gradually. So the icebergs were able to travel much further than what we simulate. And this has been a problem in past simulations as well. So the two lines are from my model runs from the modern day simulation or the Ice Age simulation, and they never make it far enough. So what are we missing? Why did they make it further? And I think I found a potential answer to this question. And I think that the GCMs are missing, or our iceberg models are missing a process that happens in the upper ocean. And I'll tell you about this process right now. So next slide, please. So here on the top left, we start with one single iceberg that is melting in the summer. And then as we come to winter, you would think it doesn't melt as much anymore, but actually in plot 4, you see that in winter, the North Atlantic is much stormier, so you get much larger waves and you actually erode this iceberg much quicker. So in fact, even though it's colder in the winter, icebergs deteriorate faster in the winter than in the summer. So in step 5, in the next summer, you're not left with a lot of iceberg. Now, next slide. If we start instead with an armada of icebergs like we probably had during the Heinrich events, we would get a lot of summer melt and stratify the upper surface of the ocean. And this very fresh stratified surface layer can grow sea ice during the winter. And the sea ice very efficiently dampens out the wave erosion. And so you're left with a lot more iceberg in the next year. So next slide. When I turned off the wave erosion during 4 months of the winter, and we did some calculations that is a reasonable amount of time that sea ice may have persisted around these icebergs, then you get the green line, which fits perfectly to the proxies that we know from our sediment cores. Now, just to finish up, there's a big caveat here. Next slide, please. These icebergs were probably really large, and we do not, so far have not included the breakup of icebergs, which is a main deterioration process. And so here, this is work from a postdoc that's been working with me, where on the top left panel, you have icebergs that around Antarctica, simulations that do not include breakup. And we developed a parameterization to include breakup. And on the right, you see the breakup version. And the gray lines underneath are the actual observed icebergs. And so we get a much improved iceberg representation. And that has far-reaching implications on the freshwater distribution that you see beneath. So that is to say, my simulations from the original paper that we published on this are probably wrong, and we're going to have to all do it again with the breakup parameterization in the iceberg model. Thank you.
Thank you very much, Till. We got time for a couple of questions.
I have a quick question, John. Michael Morgan.
Yeah.
Hi. So thanks for your talk. I was curious, how much what's the effect of all that ice in the North Atlantic during these Heinrich events in terms of changing the storm track? I'm wondering, the breakup of the ice due to the wave action and all that is probably somewhat related to the action of sort of the mid-latitude and eddies that are going across the Atlantic. I'm wondering, do the paths of those eddies actually change because of the ice?
Yeah, so that is a really good question, and that's also another project we're working on right now. Is that the limitation of my simulations here are that the icebergs are not online, right? So we take GCM output and we run the iceberg module independently, and so I'm not able to really talk about the interactions from my model runs. We know from the LGM reconstructions that the winds in general were stronger in that area during the LGM, but that's kind of all we know. And I don't know whether that's an impact of all the ice or whether that is a result of other large scale changes.
Thank you.
Brad, you've got your hand up.
Thanks. So Till, if I understood you right, you turned off the wave term to capture the right. Are you in the process of developing a parameterization that would actually get the freshwater and more sea ice formation?
Yeah, so that's really challenging, because you basically need to, so the GCMs struggle with the halocline with a thin surface layer, even in the modern day Arctic. And so to get this at that sort of level resolution, a fresh surface layer that can grow ice in the actual GCM is really tricky. And so that's why we think that they haven't been able to capture that in past model runs. We've seen some indication that this process happens in fjords and observations around Antarctica, but it's really hard to capture that in the GCMs. And I don't really know, unless we like improve resolution and a general representation of the surface processes, it might be tricky to actually capture this.
Thanks.
And Liz, by some perverse situation, we've got our two newest faculty members at the end of an alphabetized list, and I will not restrict them from answering questions. So Liz, go right ahead.
I'll keep it quick. This is cool, Till. My question is more related to any ocean biases that there might be in CCSM4 versus CSM. In particular, we know that there's huge biases in the Gulf Stream and North Atlantic current path, at least in pre-industrial and historical simulations. And I'm wondering if you've thought about that and how it relates to how far the icebergs can make it or not.
Yeah, so I think the main bias that I am curious about and that I have not constrained is the how the sea ice looked like in the North Atlantic in the LGM. That is really badly constrained in CCSM4, and so there are some reconstructions that are supposedly better, and so I'm hoping to rerun this with more than just one forcing to see what the biases are going to have, what effect they'll have. For now, we've just used CCSM4, but that's definitely a limitation.
Thank you very much, Till. And I think we're going to move on to our last speaker of the day, but by no means the least of our speakers, and that is our brand new faculty member, Hannah Zanowski. So Hannah, we're very happy to have you, and I'm going to hold you to the 5 minutes, but I'm not going to hold you to the question time like I didn't do to Till. I'm going to make sure you guys get all the questions you can. So take it away, Hannah.
All right, thank you. Yes, happy here to wrap things up with everybody. So if you can advance my slides, please. All right, so if there's one thing that I'm, most interested about the ocean, it's basically understanding how sort of changes that happen in the polar regions are actually communicated to and transported in the deep and abyssal ocean. So in particular, I'm actually interested in Antarctic bottom water, which is a water mass that is formed around Antarctica, as its name suggests. It is extremely cold and dense, and as a result of that, when it's formed around Antarctica, it then sinks and spreads out into the global abyssal ocean. And so this is just a figure of the fraction of Antarctic bottom water in the abyssal ocean, so the fraction of the water below about 4 kilometers in the deepest parts of the world's oceans. And those blue colors basically indicate that there is more of that water mass present as you get into the darker blue range. And so what I really love about this picture, this is from a paper by Greg Johnson, is just how sort of pervasive, if you will, this water mass is across our planet. And it's something that is really interesting to me, especially when I think about understanding sort of past, present, and future abyssal ocean circulation. If you want to understand that, then you need to understand what happens with Antarctic bottom water. Can you click once for me, please? Now, naturally, since I am interested in that, I have actually spent an inordinate amount of time not doing anything research related to Antarctic bottom water. I started out by looking at abyssal ocean temperature changes as related to some changes that happen in the Southern Ocean, including Weddell polynyas. And these are these big holes that open up in the sea ice in the wintertime in the Antarctic. Polynyas also occur in the Arctic as well. Some of the other things I've worked on, just to give you an overview, I've worked on putting in sort of this hybrid tracer into an ocean model to kind of understand ventilation in the ocean. I've used high resolution models to look at West Antarctic temperature variability on that continental shelf in terms of the ocean. I've even done some observational work, which was a big change for me in my previous position, where I looked at equatorial Indian and Pacific velocity variability using Argo floats. And more recently, I've moved all the way to the Arctic, where I've been looking at freshwater transport in and out of the Arctic in CMIP6 models. So kind of looking basically at the ice and the ocean components of freshwater and trying to understand the present and future changes that we might expect in the Arctic as well. And so like Ángel, I have this paper in review, but unlike Ángel, I did not get reviewer comments back today and instead had to send a lovely email to JGR Oceans reminding them that I do exist. So maybe I'll get reviewer comments one day. But next slide, please. So I'm currently working on a completely different project right now. And that is, I've decided to go into paleoceanography. So currently I'm trying to understand the ocean circulation during the deglaciation. So basically from about 22,000 years ago at the last glacial maximum, all the way up until present day. And I'm looking particularly in this ocean-only coupled model where it also has isotope tracers in it, which are basically kind of tell us a lot about how the ocean is ventilated or how the circulation is changing over time. And so this figure over here is kind of showing some of that, where we have changes in the Atlantic meridional overturning circulation in the Navy, and then the carbon-14, which is just one of these tracers that we have in this model in the yellow, and that's the atmospheric evolution of that. And carbon-14 is a really cool tracer because it is radioactive, so it decays over time, and there are no sources inside the oceans. The ocean takes that up and sort of it spreads around, it decays, and we can kind of get an age of the ocean water, if you will, from that to get a sense of what the ventilation is. And so that's what I have on the right here as a figure of the zonal mean carbon-14 age in all of the sort of main ocean basins, the Pacific, Atlantic, and Indian Ocean. Going down in time, so or increasing in time, so from 22,000 years ago all the way down to the bottom at present day. And just what I want you to take away from this figure is you can see that your age sort of gets younger and younger over time, and that's just an indication of things being better ventilated in present day circumstances. So there's a whole lot of stuff actually in these figures that I'm kind of sweeping under the rug. A lot of really interesting stuff to kind of think about here, but next slide, please. I don't need to go into too many details about that. So thinking about where I want to go though, I'd actually really like to go back to some of my abyssal ocean work, thinking about ocean ventilation, so again, back to the abyss from whence I came. I really am interested in thinking about ocean modeling of icy worlds at some point, and I'd also like to continue with my Arctic freshwater. But knowing me, I might end up doing something completely different from all of these three things. So I'll leave it there and take questions.
Okay, thank you, Hannah. We've got time for questions for Hannah. Elizabeth.
Oh, I was just clapping, but I can't ask a question.
That's right. It's not the hand raise. Sorry.
That's okay. I'll ask a question anyway. So something I've only recently started to appreciate is the difference between ventilation and transformation. And I have almost no expertise in the Antarctic. So I was wondering if you had any comments on that.
Yeah, that is definitely a tricky one because you can ventilate through transformation that is not directly contacting the surface. I've actually also been thinking a lot about the definition of ventilation itself. Like, do you actually mean water has reached the surface and equilibrated with the atmosphere? Do you not? Because we kind of use ventilation interchangeably in kind of a weird way. And there are definitely times where you can get changes in age tracers that are decoupled from the changes in overturning, which is what we typically ascribe to as causing changes in ventilation. So I am still actually hammering this out in my own mind because I think there's a lot of really interesting things here, and especially in terms of how we interpret and understand age tracers in the ocean. So I'll leave it at that, Liz, but yes, there's a lot to unpack there.
I've got, thank you. I've got Dan and Brad for questions. Brad, maybe you can go first.
Hannah, I wanted to go back to the abyss, and I was wondering why there's such a sharp discontinuity right at the equatorial Atlantic. Is that bathymetry, or why does it go from old to very, or a high percentage of Antarctic deep water to very little?
So it does that because the densest water mass in the North Atlantic is North Atlantic deep water. It is not Antarctic bottom water. So that's basically the only other place where we have dense water formation in the oceans in the North Atlantic. And so when we think about water in the bottom 4 kilometers, some of it that fills up in that region is actually North Atlantic deep water, and Antarctic bottom water does not sit below that water mass. In fact, it kind of disappears in that region.
So why so sharp right at the equator?
Why at the equator? There is a fracture zone there, so that could be it is partially bathymetric there. And so kind of thinking about in the Brazil basin, which is that last blue basin on the left that's furthest north in that figure in the Atlantic. So that actually does have a lot to do with it as well. So.
Thank you.
And Dan, question.
Yeah, that was, it's fun seeing all the cool things you're doing, Anna. Why is the ventilation so much larger during LGM? I would have expected the opposite, and maybe that's because I don't know what I'm talking about. But maybe
no, the water was older, so it was more sluggish. So that's kind of, if I said that wrong, I totally apologize.
No. What do you mean by that?
So when you have technically you have less ventilation when your circulation is a little bit more sluggish and you're just not doing a ton of overturning in that time period.
Why was the circulation more sluggish during LGM?
Yeah, so sorry. So you were asking me why things were better ventilated during the LGM, am I understanding you correctly?
No, I thought I saw that it was
Yes, yeah. So it's not as well ventilated. And again, that is partially because of using the carbon-14 tracer. This actually has to do with sea ice to some degree. And so this is a question that we're still trying to figure out. Is again, this sort of decoupling of the circulation itself from the sort of surface actual sort of uptake in the atmosphere. And so you can kind of look at different tracers like ideal age, for example, Dan, where you won't necessarily see as much of that. It also depends on the ocean model. So again, I know in this model, there are definitely biases in the Pacific in particular, where things are a lot older than they necessarily should be. But at the same time, which is a bit of a conundrum, I've also been told that this particular class of the CSM has more vigorous circulation at the LGM than it should. So again, still trying to figure out some of the things that are going on here. But yeah, it's very, very curious.
Thanks.
Mm-hmm.
Okay, any other questions for Hannah? Well, okay, Hannah, thank you for an excellent talk, and all of our speakers for excellent talks. And I'll also say thank you to the audience for hanging around an extra amount of time. It's really not something that anybody wants to do to cut people off, especially when we're being reminded what a great department we have because of all the various scholarship that's going on. Just as Dan mentioned, in honor of John, he would have been thrilled to be here today and to have seen this. So it's just fantastic. We've got a new dawn, and some of that dawn was described by some of our brand new people today. So we're very happy about it. Next week, we have Abigail Swan at 3:30 on Monday. and that will be exciting. I think Bailey sent an email around about scheduling visits. So you might want to take a look at your email if you want to talk to Abigail during the day next Monday. So we'll see you all then. Zoe, thank you so much for organizing this marathon session. And again, to all of our speakers, thanks very much.